All right, welcome to the chapter F5.1, Raster Vector Conversions. Thanks for the introduction, Jeff. We have written these scripts a little more than a year ago. Very excited to have this opportunity to walk through the sections. My name is Keiko Nomura. I'm the Director of Science Applications for Climate Engine. And
hi, everyone. My name is Sam Bowers, formerly of the University of Edinburgh, but presently of WWF in Denmark.
So let's start.
So this chapter has quite a simple objective. It's just to review methods of converting between the two main forms of geospatial data that we get, between rasters and between vectors. What's more, we're going to show you a few examples of situations in which this is useful. In order to do that, we're going to focus on a range of really quite well-known data sets. So we're going to look at topographic elevation, we're going to look at forest cover change, and we're going to look at protected area database. Between them, these span a range of raster and vector data sets that are quite useful examples of how these sort of situations will work. So in terms of learning outcomes, we want to understand raster and vector data and their differing properties and how we work with them on Earth Engine. We want to know why would you convert from raster to vector and how. We also want to know how and why you'd want to do the inverse to convert from vectors to rasters. And finally, we're discussing a few of these commonly used methods in Earth Engine, such as writing functions and mapping it over a feature collection. Now, there are a few prerequisites for this chapter listed below. It probably doesn't stand on its own, so we'll skip over some of the details, which maybe you'll want to look back on first. However, we'll try and keep things accessible, and we will reference other chapters where we're able.
Okay, so before diving into the practical applications, let's go over what are the raster and vector formats and why are we converting them. Many of you may know, but let's just start with raster data. The typical raster data looks like phone images, like images from your iPhone, or it could be a satellite images. It consists of pixels and information is stored in each pixel. Vector data looks more sort of like a boundary data. For example, the figure in the middle of this slide, it's showing US county boundaries. So it consists or contains of geometry features, lines, polygons, or points, and for specific locations and areas. Typically, raster and vector data are used in combination. Both of them are used. For example, raster data, which can be temperature data on the left here, and then vector data can be state borderlines or city points, and you want to get the temperature data of that particular city or particular state, and you use reduction to get maximum temperature of that particular area or average over a certain time period. So those are the common usage, but there are situations where you may want to convert the format from raster to vector or vector to raster. And we will try to give you examples, so there will be a context to it, and whether those are appropriate use cases, or you should just stick to the original format. It really depends on the use case. So as Sam mentioned, we will be using 3 data sets. 2 are raster data, elevation and forest change, and 1 is vector data, which is protected area. In Earth Engine, they are feature collections, and we will be converting between the formats and in these specific contexts. So we hope that will make sense to you. Many of you may know, but there are repositories to the script we are showing today. And on the right side, I'm showing how it looks on your code editor. The only difference is that in your case, instead of writer folder, it should probably say reader. And today, our section is F5.1, and we will go over each checkpoint. And if it may not show up immediately, if it doesn't, please click refresh button, maybe more than once. Sometimes it takes a little bit of time for this to show up. And if you are a beginner or if you need help, there's a very good documentation on the Earth Engine website. So please look at those as well. Now let's start with practical applications. So as I mentioned, we will be using elevation data for this exercise, and we will be focusing on Colombia as a location. So hopefully now this changed to code editor screen. And I'm just going to run this quickly. So elevation data, it looks like this. And I'm zoomed into Colombia. When you click this with inspector, it's going to show elevation in meters. It has different elevation information in each pixel. Now, so this is a raster data. When you want to use vector data for this type of information is when you use threshold of certain elevation and you want to see, for example, elevation above 100 or 200 and how that's going to create new shape in this map of Colombia. So instead of these contiguous values that the raster has, vector, as we mentioned before, it tends to have a geometry like lines, points, or polygons. So let's first convert this information of continuous values into some sort of categorical classes. So there is a very useful function in Earth Engine called where. So where you can use it to make a zonal map out of this elevation raster with many different values. So for example, here I'm saying if elevation is more than 100, I'm calling it zone 1. If it's more than 200, 2, then 500, let's call it 3. So I'm creating 4 different categorical classes for this elevation data. So how do they look like? Now it looks like this 4 different colors in elevation, still based on this original data, but it's much more simplified and it started to have a shape, geometric features. So this is a type of map you may want to convert to vector. The use of it is, for example, you are interested in different canopy cover percentage depending on elevation zones. Then if you make this into vector, you can use those zones to extract information of these zonal areas. So now this zonal map, let's convert to vector. So this is a highlight of this section, and it's pretty easy. In Earth Engine, you use this function reduce to vectors. And there are lots of options here, which you can look it up in the documentation. But what's important here is you will make sure to choose polygon as geometry type because they are not lines or points, they are polygons. You are converting them into polygons. And then how do they look like once you convert to polygons? Now it does have lines. So this is now a vector data. If I zoom in, you start to notice it's really complex lines, complex vertices, because it's converting the pixel as lines and polygons here. But you may just want to have much more smoother lines. You don't care accuracy of particular areas based on pixels, but you want to create nice looking, easy on the eye vector data of elevation zones. For that, you can use focal mode function. This was covered in one of the previous tutorials, but this is a morphological operation. It simplifies the shape by using pixels around the pixel. In this case, I'm using 4 pixels around the pixel and smoothing the lines, simplifying the shape. Now, if you do so, this is how it looks like. and compare to the original line, which looks like this, the edges are a little sharper. Now, new one looks much more smooth and started to have little even more vector-like features. There are lines and boundaries. So then now you can also reduce this raster data into vector and create much smoother elevation zonal polygons, which looks like this. And hopefully both gonna load very fast. But compared to the initial elevation zonal polygons, which looks a little more pixelated in a way, now this new one looks more like geometric features. So this is how you can convert raster to vector in terms of polygons. Now, next section, I want to show you how to convert to points data. So for that, let's zoom into a much smaller area in Colombia. And you may wonder, why do you ever want to convert to points? Well, you may be surprised, but more often than not, there are instances where such point data would be useful, especially for people outside of remote sensing community. Businesses and organizations, the way they process data is in a tabular format. If you want to take information out of Earth observation data, the window is really actually a vector format. So selecting this particular area, this is the area, by the way. So I chose very limited, smaller area here. And I want to convert each and every line of this elevation data into points so that the user can see each and every single value of elevation based on the coordinates. So the way to, there's more than one way to do this. And here I'm showing how to do it with sample function. I chose this function because I find it, this is very intuitive, simple and fast and light. And the important thing here is you must use the raster's native projection and scale. And also you need to turn on the geometries option. Without this, it will return the values without any coordinates information. And when you do this, it's going to convert information into the points. So as you can see, it's getting the centroid, center of each pixel as points. And it was, as you can see, very instant. It's very fast. And since you are doing this typically because you want to give this data in an Excel file for people who it's easier to use, so you may want to reorganize this data. So next several lines is to do that. So you add column names like elevation, longitude, and latitude. So organize output in that way, and you can simply export to Drive. Now this is the CSV file. And another sort of bonus function I wanted to mention is stratified sample function. So sample function can randomly select points as well, and stratified sample will also randomly select points, but you can specify number of points you want to sample, and also per each, for example, zones. So here I set up 4 different zones for this elevation data. And if I say 10 points and then per zone, it will randomly select 10 points per each zonal areas. This is particularly useful if you are looking for more balanced sample points. So I wanted to mention this sample function in addition to sample as extracting points data. So now that's the end of 1.2. Over to you, Sam.
Just give me a second to pull up the slides. Oh, you will see my screen still.
Yes.
Okay, thanks, Keiko. So what Keiko has shown you there are some fairly basic applications of converting between rasters and vectors. What maybe is a little bit trickier is trying to identify in what situations you might want to do these operations and in what situations they are best avoided. Now, the way I'm going to do that is I'm going to show you another code section, but this time using some slightly different data, the Global Forest Change Dataset and the World Protected Areas database. So first, let me introduce these two different datasets we've got. What I'm showing on my screen now is the deforestation dataset from the Global Forest Change dataset. You're seeing a lot of different colors here. They range from yellow all the way to red. The yellows indicate locations that were deforested way back in 2001, whereas the reds show locations that were deforested in the past few years. Now, if I zoom right in on this, you'll see what the data format is. It's a raster. So we're talking about these large grids of points, each one which is labeled either as not deforested or deforested, or where it is deforestation, it's labeled by the year it was deforested. The second data set I've got is the protected area. So this is a protected area in Colombia. It's called La Paya. And this is a vector data set. It's a polygon outlining the location which forms part of the protected area and which parts are outside it. So these are the two example data sets that I'm going to show you that indicate how you work with these two different formats and how you convert between them. So first up, we load the data sets into Earth Engine. We can print to show what they are. So we've got one image, one feature collection, that's the raster and the vector. Now, the key part of this is converting from raster to a vector format. And we do that with the same function that Keiko just showed, named reduce to vectors. So deforestation is our raster. We want to reduce it to vectors. And we have an array of properties that we need to specify. The important one here is the label property, in this case, loss year. So for each polygon we're getting out of this process, we want it to be labeled with the year of deforestation. Now, let me show you what these data actually look like in vector format, because it's quite different. So I'll zoom onto that same location as before. This is showing the raster. And when it loads, this will show the vector outlines. So you'll see the data format is quite different here. We've just got the deforestation areas which are loading into place now. Or some of them are in any case. Let's show you over here. So now we've gone from the individual pixel values to outlines of areas of deforestation. Now, the reason this works without the additional processing that Keiko did is this raster is a categorical raster, whereas the elevation data set we were looking at earlier was a continuous raster. Now, the importance is it means that we have these contiguous areas or shapes which have this vector-like property, which means that this conversion does tend to make sense. The situation you really want to avoid is converting to a vector where you have continuous data pixel values. This will look very strange. You'll end up with a series of outlines, one per pixel, and this is not a useful data format to be working with. But where you have contiguous or homogeneous areas which can be labeled and outlined in a shape, that tends to be a reasonable thing to do when you want to convert to a vector. Now, this is showing you what has been done, but maybe it's more relevant to show you some of the applications of this. So the first one I've got is we can now calculate the number of unique change events. So when we add up the number of distinct polygons we've got, we can identify that in the La Paya National Park, there were 8,000 unique change events. That is an operation that you can do on a raster, but it's far simpler to be doing it when you have a vector data set. We can also graph these over time. So here I've got a plot of all of the number of change events over years, and we're seeing that the number of unique changes is increasing year on year, all the way from 2000 to the present day. There are some other things we can do too. So here I've extracted what's called the centroid. So for each of these polygons, we can extract just a single location that represents where the changes took place. So now we've gone all the way from a raster data set to a series of point locations. Now, there are good reasons you might want to do this. For example, if you are planning a field campaign to identify what the drivers of change are in this area, you could convert them to point locations, which indicate where the change took place, and go into the field and identify what might have caused it. The final output here is we can also use this new data set to extract just locations which meet certain properties that we're interested in. For example, we may be interested in identifying where are just the largest of changes, just those changes that are greater than 10 hectares. The way we have done that is you add a new property to this feature collection. That property is the area. And we can use a standard filter to remove any polygons that don't meet that criteria. Now, again, this is possible to do using raster data, but it doesn't tend to be as easy. And there are real useful properties that are uniquely available from a vector data set that would justify this conversion. Now, the final thing that I will mention about this section is there are potentially reasons you might want to output your raster data in a vector format. This is a really nice means of visualizing data, and it can be far more appropriate for some forms of visualizations than others. So it might also be, rather than an analytical step of your processing chain, it might be the final output that you want. In all these cases, the first step is going to be using that function reduced to vectors and applying it to a raster. So I think that takes me to the end of this section. And we'll move on to the next section, 1.4. Now, there is one mechanism that I didn't mention here, and it's not truly a conversion between raster and data formats, but it's a very, very common application of combining raster and data formats, and it's zonal statistics. Now, this is going to be discussed in far more detail in a future chapter, but I think it's worth mentioning at this point, just so that you know how it is done. So I'll return to the code here. Now, we're using exactly the same data set as in the last section, the global forest change data set and the WDPA protected areas data set, but I've expanded our analysis slightly. So we were initially looking in just La Paya. In this case, we're looking in 6 protected areas across the Colombian Amazon region. Now, one question you might ask as a manager of this area is which of these protected areas have deforestation that is occurring in or nearby to it, and what rate of change is associated with each. Now, it's possible to get this information out of a raster data set, but normally in this case, you're talking about identifying some property as defined by a polygon. Now, the way we do this is we attach a new property to our vector data set. So this is the WDPA data set. So first we're producing a subset, which is just looking at these 6 protected areas we're interested in. We are interested now in the reduce regions method. That's the same method that we use to extract the raster information and apply it to the vector data set. So what we're getting is a new property. It's called deforestation area, which relates to how much forest cover was changed inside of each of these polygons. Now we can turn that into a deforestation rate. So that's dividing the amount of forest change by the total forest area. And we end up with a feature collection or an object which contains new data. So in this case, we've got a list of each of the protected areas, all of our 6 protected areas, and in each case, a deforestation rate expressed in terms of percent. So it is the Tinigua protected area that's experiencing the most rapid rate of change, and the most stable area is this 4th one, Serranía de Churibiquete. So that takes me to the end of that section, but I've got one more before I hand back to Keiko. What we've discussed so far is how we convert from a raster to a vector. But there are just as many situations in which you might want the inverse operation, which is converting from a vector dataset to a raster dataset. Now, I do this a lot. As soon as I'm handed a vector, I'm very, very quick to rasterize. And there are particular efficiencies that I gain by doing so. But there are lots of reasons that you may want to do this. Probably the most common is to apply it as a mask. So for example, you may only want to extract the information contained in a raster that exists within a certain polygon. And to do that, you can apply a mask. So returning to the code, let's take a look what we've got. So again, we're using the same data sets here, the global forest change data set and the protected areas data set. We're looking over an area which is far bigger here. So this is a fair chunk of South America. And what I've done is the inverse operation. So this is the conversion from vector to a raster, and it's called reduce to image. Now, one thing which maybe is a little bit unclear to a new user, but makes a lot of sense, is you need to express which property it is that you want to apply to the raster. So in this case, I've applied a simple property which is called protected. So I've mapped this function which gives every feature, every polygon a value of 1, which indicates whether it's protected. And then I've used this reduce to image method to burn it to a raster. So what we get is an object called WDPA mask, and it is 1, or shown in white here on the screen, wherever an area is whenever a pixel is inside a protected area, and it's black wherever it's outside. And just to convince you that this is indeed a raster, we can zoom right in, and we can see these new pixel boundaries, which appear once you've got these data in the right format. Now, let me show you an example of why this might be useful. In the WDPA protected area dataset, each unique protected area is given a unique ID. So this is in the final bit of the code. So we can produce a raster which can also be used to determine which protected area is associated with which pixel. So in this case, I've colored each of our pixels by the protected area that it's associated with, which means that you could, in a script, refer back to which protected area each is. Now, the final part of this is we can use this mask to produce some useful data. So here I've used the deforestation data set that we were looking at earlier, but I've removed all deforestation that occurs outside of a protected area. So the part of the code is here. So deforestation, wherever we don't have this WDPA data set, is removed and set to 0. So this is a way of producing a raster data set that has all the deforestation removed outside of a vector, but you could do the return reverse as well, just as easily. So that's just a quick introduction to the methods of converting from vector to raster. I'm going to return to Keiko now, who's going to show you a far more complex example.
Okay, great. I'm going to share my screen now. So I'm going to use a little bit of everything we covered so far, especially the data set that Sam has been using, the deforestation data and also protected area vector data. And for this complex example, I'm going to use one of the protected areas from that WDPA data set, and I chose La Paya as an example here. So this is still about vector to raster conversion. I also increased the font size based on the comment we received in the chat. So after you selecting La Paya, which is still a vector data, and Sam showed you how to convert such vector data, polygon data, into raster data and use as a mask. And for that, he used reduce to image function. Now, there's other ways that function returns to image from vector, which is distance function. This is particularly useful for protected area or forestry management operation where you are interested in like buffer zones or protected area, for example. So what it does is it takes, in this case, feature collection vector data, and it returns a raster image including a distance information from that vector line. So here you set the maximum distance you want to include in this new raster image. Here I set really large number, 1000 kilometer, and then it looks like this. So the highlighted areas are the boundary of this lapaya. And if you click here, for example, it shows, okay, it's about 7 kilometers away from the border. And if I get closer, it's about 1.5 kilometers. So this is a raster data that returned from a vector data. And let's keep using this for another example. Let's see if you want to show this sort of distance information, visualize them, but only inside the protected area. Then go back to what Sam did with the masking of this raster data from the vector to rasterized data. And we can show, okay, this is just inside. So you use a masking technique to show only the inside. And now if you want to show the outside, only mask accordingly. So now you can see how only about the outside of the boundary and the distance from the protected area. And then if you remember how I did the elevation zonal data, same kind of techniques can be applied here. You are more interested in the zonal area around the boundary where it's about 1 kilometer around the boundaries, or 3 kilometers or 5 kilometers. You can do that, again, creating a zonal raster map first. And that will look like this. So now instead of continuous raster values, now I have converted them into zonal map, which is basically the buffer areas around the border. And you can take this one more step. You can combine with the deforestation data that Sam has used, and let's show deforestation within that 1 kilometer from the protected area, for example. And that will look like this. And 3 kilometers, and then 5. So this is, again, very useful tool for forest management as well, when you want to quantify how far deforestation is approaching to the protected area. Now I'm going to end this session with getting the statistics of actual deforested area. In this example, I'm going to use, okay, within the 1 kilometers from the boundary, but outside of the protected area, how much of the area have been deforested. In order to do that, you will first use that mask, the deforestation 1 kilometer, and then you need to convert that raster data into the area raster data that has the area information. This will convert to square meters. By dividing by 10,000, it makes it hectare. And you use reduce function, sum up the deforested area, you will get about 4,000 hectares have been deforested within 1 kilometer buffer outside of this protected area. So this is the end of our section.